Good evening, good morning, good afternoon, everyone, depending on where you are. Welcome everyone to the youth talk tonight. And first, I would like to introduce myself. My name is Zheng is a professor and vice dean of the School of Advanced Materials and Nanotechnology in Xidian University in China. I used to, before I joined Xidian University, I worked in the University of Minnesota, where I have won the NSF Career Award, 3M Non-Tenured Faculty Award, Nano Energy Award, etc. And first, I would like to introduce all the participants for tonight's program, and all the speakers and panelists, including the first speaker will be Chris Falconi from University of Rome to Vergata, Professor Yuebing Zheng from the UT Austin, Professor Yunlong Zi from Hong Kong University of Science and Technology, myself as a moderator. In addition, we also have two panelists. That will be Professor Yuebing Wang from Xidian University and Professor Yun Qin from Lanzhou University. And please let me first introduce our first speaker, Professor Chris Falconi from the Department of Electronic Engineering, University of Rome, Vergata, Rome, Italy. He received his master's degree and PhD degree in the electronic engineering from the University of Rome, Vergata in 1998 and 2001. He has contributed as a corresponding author and co-corresponding author papers on leading journals in nanosystems, such as nanoenergy, electronics, IEEE, PCES, sensors, and interdisciplinary journals, including Nature Communication, Advanced Material, etc. Since 2013, he is adjunct professor at the SKKU. Since 2017, he is adjunct professor at the Beijing Institute of Nanoenergy and Nanosystems. He has visited the top international universities worldwide, including the University Linköping and TU Delft, Georgia Tech, SKKU, BINA, etc. His research interests include analog electronics, electronic interface, sensors, nanogenerators, micro nanosystem, electronic device, and biomedical engineering, etc. Without further ado, I would like to welcome Chris Falconi. And Chris, please share your PowerPoint, and the floor will be yours.
Thank you very much for the introduction, and also I would like to thank you very much, the organizers, for inviting me to give this presentation and to participate to this very nice and interesting event. Thank you very much. And I would like to start my talk by thanking co-workers who contributed to some of the research I will be showing today. So starting with Professor Arnaldo D'Amico, Professor Zhonglin Wang, Professor Sang-Woo Kim, and many other co-workers and also former students who contributed to this research. Thank you very much to all of you. And I would like also to express the gratitude to funding agency which has supported our research during the years. And in this talk, I would like to discuss about the research that cross the traditional boundaries between material science and electronics. So research at this intersection is required for electronic engineers to receive new innovative devices from material scientists, and is also required for material scientists who need better systems for fabricating and characterizing materials. In fact, several scientific and technological breakthroughs occurred at this intersection, including the invention of transistors, of electron microscopes and scanning tunneling microscopes, of semiconductor heterostructures and integrated circuits, just to name a few. And also more recently, nanogenerators and piezotronics also is a growing area of research that is at this intersection. And as you see, in just a few years, already attracted thousands of papers per year. So just another remarkable example. So in this talk, I will see that in addition to these outstanding examples, there are so many other opportunities, and I will show some of what we have been doing with our teams. And I will start with how we use material science for designing some innovative electronic devices. So this is a work in collaboration with Sung Kyun Kwan University, at that time the University of Professor Sang-Woo Kim, and our university, and is about rewritable ghost floating gates that can be defined by tunneling triboelectrification. So this work started by after a previous work from the group led by Professor Zheng Wang, where they scratched an insulator with the tip of an AFM. And therefore, by triboelectrification, they created triboelectric charges that remained localized on the insulator, because the insulator does not allow conduction of current, and therefore what they found by measuring after scratching the insulator with contact mode AFM, they used the AFM in non-contact mode as a scanning Kelvin probe microscope, and they found that there was significant potential difference between the scratched area and the non-scratched area. And that is because the localized triboelectric charges result in potential difference. So we basically repeated the same experiment, but after placing a graphene layer on top of the silicon oxide. And before going to that experiment, let me mention that in this original paper from Professor Zheng Wang and coworkers, the lifetime of these stored charges was in the about 1 hour or just few hours. So we repeat the same experiment, but we place the graphene layer on top of the silicon oxide. So apparently, one could think that after rubbing, that means creating triboelectric charges, there will be no potential difference, because graphene, in a way, is conductive, and therefore it should not allow localized charge to survive. The potential difference should disappear because of the conductivity of the graphene. But actually, as you see here, we found that after rubbing, there was significant potential difference, and similar to the previous work from Professor Wang. So what happened? We also measured the potential along this x-axis, so along a line. And as you see here at the bottom left figure, we found the potential difference. So this is the x-axis and the potential that we measured. And initially, you see the red curve, that is the rubbed region, has a higher potential in comparison with the unrubbed region on the periphery. But after very long times, here, for instance, after 72 hours, so much longer than in the previous experiments by Professor Wang and coworkers, we still found significant potential difference. So not only we found a potential difference, even graphene is conductive, but we even found that this potential difference survived for much longer times. So here you see the potential difference as a maximum potential difference as a function of time. Even after 72 hours, you see after an initial transient that is fast, there is a very slow transient, and it can go for days. So what happened? We propose that the triboelectric charges that can be generated by scratching the AFM tip with the graphene layer can be very easily injected through the defects of the graphene, because graphene is so thin, so just one atomic layer, so tunneling is very easy and effective. And these charges that can flow through the graphene, they can tunnel through the graphene, they can be trapped at the air silicon oxide interface underneath graphene, and those charges can act like a ghost floating gate. So it's similar to the charge that are generally placed on a material, real, concrete gate, like a metal gate. In this case, we don't have any metal gate, but we have some charges that are trapped on an insulator at some very small distance from the material, that in this case is graphene, and can still act as a ghost floating gate. We call ghost because there is no material, it's just the charges on an insulator. And these charges on an insulator, we can create, delete, and recreate at will, so that we have some ghost floating gates that can be defined on demand. So unlike the conventional material gates that are fabricated once forever, these gates can be created, deleted, recreated, modified. One can modify the area and so on. So with this model that you see here, we also understood why the lifetime of these charges was so long. And the reason is that there is, yes, the silicon oxide insulator, but also air that is better than silicon oxide as the insulator. So this is the capacitor that discharges very slowly, and therefore that's why the lifetime is so long. And here are some additional experiments. We repeat the experiments with biasing the AFM tip, and in this way we obtain different charges of different signs. And here, this is also another interesting experiment, because you see, by changing the biasing potential of the AFM tip, we can create PP plus junction or PN plus junctions. So interestingly, with this method, one can create, modify, and destroy PN and N regions at will. The spatial resolution can be very good because it's related to the spatial resolution of atomic force microscopes. The PN plus and PP plus junction that we created are rewritable. And also, one can think of time-variant 2D electronics, where conductors P and N regions can be defined on demand by this AFM tip. It's also interesting to say that AFM tip can be integrated on chip, as for instance, there has been a lot of research a long time ago, and now again from IBM on the so-called millipede, arrays of AFM tips that can work independently, all integrated in a chip. We also repeated the same experiments on other insulator, always with graphene. And then we also proposed that different 2D materials could also be on the same substrate, and also that multiple AFM tips could be used. So this is just one example of material science used for fabricating devices that could not otherwise exist with conventional microfabrication technique at this time. This is another work also in collaboration with Professor Sang-Woo Kim, where we use the same concept, but instead of creating the ghost gate underneath the 2D material, we this time use PDMS layer on top, which is very robust device. And by touching the device, we create triboelectric charges that even at this time can work as rewritable floating ghost gates. So another example, and we use this device as a touch memory that can be written without any connection of the device to the power supply. So it's totally zero power for writing. But of course, for reading the touch memory, we do need a connection to the supply voltage. So just another example of rewritable floating ghost gate. This is another more recent work. And here, we wanted to take advantage of the many properties of LDH, layered double hydroxides, that can be very easily grown with high density and relatively good alignment. They can be very thin. Then the small thickness has been predicted to give important side effects for pyroelectric nanogenerators. And also, LDH are very flexible. There are many degrees of freedom for tuning their properties, because one can choose different M2 plus in this label at the bottom, so different bivalent cations, or different metals, different trivalent cations, different anions, and also different levels of hydration, and also different ratios between the divalent and the trivalent cations. So really is a material which offers lots of flexibility and possibility to design. Besides that, it's also very simple to grow with wet chemical methods on just aluminum substrates. So if we use that approach that we consider in that paper, there is another advantage, that we get high gradients in the composition and also, therefore, in the energy levels. in the nanostructures. Very simple. So to test these ideas, we just use very simple wet chemical process, just one process to grow on aluminum substrate, the LDH, and then we just deposit very thin top electrode metal. And then we test as a pyroelectric nanogenerator. So here you see example with zinc aluminum LDH. And as you see here at the very bottom left, these three figures represent the test with sinusoidal temperature variations. And as you see, the derivative of temperature with respect of time, of course, is also sinusoidal, but with 90 degrees phase shift. So, and then you see that the current is very accurately proportional to the derivative of temperature with respect to time. That is this output current is truly a pyroelectric current, and also the pyroelectric coefficient is positive. Then, as another example, here also very interesting to see that we measure the composition as a function of height, and as you see, there is lots of aluminum at the bottom because it's close to the aluminum substrate, and when we go up high, we find less aluminum and more zinc because, of course, of the growth of the nanoplatelets. So there is a significant composition gradient that is also expected to improve the pyroelectric coefficient. Then we replicate exactly the same experiment, but with including magnesium instead of zinc as a salt in the nutrient solution. So we get magnesium, aluminum, LDH, and as you see, again, in the left bottom figures, you see the sinusoidal temperature variation, derivative of temperature with respect to time, but this time, the output current is the opposite of the derivative with respect to time of temperature. And that means that the pyroelectric coefficient now is negative. So by just changing the divalent cation, we can change the pyroelectric coefficient from positive to negative. So this is also quite interesting and confirms that the strong variability of the LDH can be used for obtaining pyroelectric nanogenerators with significant properties. I will not discuss the piezoelectric nanotransducers, but it's another example how material science can provide very interesting devices. But I will just show some of our work on the fabrication of these zinc oxide nanowires to make devices for electronic systems. So here you see some zinc oxide nanowires schematic diagram grown on a substrate. And our goal in this work was to combine these nanowires with just conventional electronics that is fabricated and assembled on printed circuit boards. So this was our idea, to grow the nanowires and then to assemble the device by just placing another substrate with some polymer in the middle to make a sandwich, and then have a device on the PCB. Then for convenience and also reliability, including to obtain matched temperature coefficient of expansion, all the substrates should be similar. And that means both PCB. That is not simple to fabricate because we need to grow the nanowires on copper. And also we would like to have dense nanowire and long nanowires to avoid short circuits. And then that is not very easy on copper, but by some design of the wet chemical processing, particularly by using potassium permanganate to avoid the fabrication of high temperature seed layers. So just room temperature potassium permanganate. And we also add some other potassium chloride and to the reference solution. And we finally find zinc oxide nanowires that are so dense and so high that can be very easily packaged with the approach that I just suggested. With this approach, we could fabricate this bracelet that is entirely just the conventional flexible PCB, and we use it for monitoring the earth bit rate. We just other electronics integrated on the same PCB. But interestingly, to check that the quality of the device was very good, even with this very simple packaging, just have the nanowires and package with another PCB on top. So we, of course, that's why we didn't want the tapered nanowires, because otherwise the top contacts would be not very good. But with our process, we got very good top contact. In fact, you see, we could use these devices also as flexible heaters with remarkable current densities that were comparable with conventional commercial flexible heaters. And this is another work where we also wanted to take advantage of electronics for growing nanowires. And we noted that generally the wet chemical growth of zinc oxide nanowires is very convenient for several reasons, including low cost, simplicity, possibility to grow on large area on flexible substrates. But there is some problems with efficiency. In terms of energy, chemicals, time, length, only short nanowires can be grown, and also cost in terms of reagents. So what we did is to try to change the conventional wet chemical procedure that consists in heating the entire container of the nutrient solution. Because if you do that, of course, there will be reactions even in the container far from the substrates. So you will waste a lot of reactants, and that's part of the problem. So we review the many approaches that have been proposed in the past to improve this efficiency in some ways, but we could not find a technique that was good in all possible points of view. So we propose that we can just take advantage of a heater that is placed in good thermal contact with the substrate. And in this way, we can have convective flows that can be strong enough. You see here the FEM simulation and also eye inspection reveal that the velocity can be easily up to 2 centimeters per second in proximity of the substrate. And this convective flow helps to continuously mix the solution, and also to improve the growth of the nanowires without any seed layer. In addition, we don't have lots of reaction out far from the substrate because the rest of the solution is kept at just room temperature. With this approach, we could grow nanowires which were very long. Here you see even tens of micron up to about 80 micron with different concentration, temperature, and growth time. But even very important, we could grow high-density zinc oxide nanowires on different materials without any seed layer. So just high density just because of the convective flows. And this is also an interesting example because you see here just a conventional flexible PCB, printed circuit board, and we could grow the zinc oxide nanowires even on the plastic of the PCB. So here you see we could have a continuous film of zinc oxide nanowires between copper track on the plastic of the PCB up to the other copper tracks. So in conclusion, with just very simple wet chemical process, we could just fabricate directly the device without any need for placing a top electrode, packaging. The only packaging that we can need maybe some closure to avoid humidity and light. And with this simple device, as you see, we get very high responses to very small strain, and that's because it's a piezotronic device where the junctions are crucial for obtaining very high sensitivity. So this is a very simple example. And here, just very quickly, let me mention, we also fabricate a self-powered, transparent, flexible graphene microheater where the high resistivity in comparison with the metal of graphene was useful to match the output, to kind of adapt the large high output resistance of triboelectric nanogenerators with the resistance of the heater. With this approach, we fabricate a flexible and transparent microheater. The HBN was required for passivation on top, and here you see some characterization of the microheater, including under strain, and also this is the first sound-powered triboelectric triboelectric powered microheater. You see, we could power without any connection to batteries or to other electronics. And now let us see some example of how we used electronics for material science purposes. So one just very recent example is we characterized some batteries. And here you see standard lithium iron phosphate cells. And we measure the noise. So just measurement that are a little, you need to be a little careful because the noise of batteries is generally very low in amplitude, but it's very doable with just conventional instrumentation, and in principle can also be integrated in portable electronics. So we measured the noise of these batteries, and we measured the noise in 2017, and you see that we measure almost constant noise for the noise down to 3.2 volt. And then when the voltage of the cell was reduced by the discharge current, we obtained very low noise. In fact, this is dominated by the instrument noise. So we could have high noise, but only for very well charged battery cells. But when we repeat exactly the same measurements in 6 years later, we found that the noise was much higher. These are dB volt root mean square per square root of hertz, much higher. And also there was high noise even when the battery cell was discharged. So we observed for the first time that noise measurements can be used for predicting the long-term calendar aging of battery cells. So just very simple electronic measurements for obtaining important information. So this is another work where we just use conventional top area SEM images of zinc oxide nanowires, and after some simple signal processing, we find the vertices in the right image, and then we find that these angles are different from the real angle, that is 120 degrees, because of crystallographic reason. With this information, we can understand which was the tilting of the zinc oxide nanowire, and with this information, simple trigonometric relations can help to find the real exact dimensions of the zinc oxide nanowire. So that's just what a scanning electron microscope conventional can do for obtaining very accurate dimensions. And let me just very quickly mention some other application, also very recent work. Here you see that we had some 4-wire measurement. That's the conventional 4-wire measurement. So you inject a current, and the resistor of interest is this red dashed resistor R. And with conventional 4-wire measurements that are available in any multimeter, you can measure the resistor R no matter the values of the parasitic resistance RP1, 2, 3, and 4. So to implement these kind of measurements with an array of devices generally take many wires and many pads and many connectors. So we try to simplify the situation by assuming that one can easily, that is generally a reasonable assumption, have the pads that can be considered as ideal short circuits. With this assumption, we can design systems where we can measure with 4-wire accurately without any contribution from parasitic independently all these resistors. So we did that. We generalized the process for fabricating such networks. And here you see a twin-wire 29 resistor network. So every single of these serpentines can be independently measured with 4-wire without any internal interconnection. With this technique and just a very simple arrangement, here you see the multimeters, but in principle, what you need is just a device on the right and just an array of switches on the left. So very simple system, and we could monitor online the 29 resistances, for instance, during sintering. Sorry, this is just this device that you see here on the left is just printed by silver nanoparticle conductive ink. So we could characterize this ink with statistically significant measurements on all the 29 of them during sintering, during change of temperature, and so on. So that is possible for all types of conductors, but we just characterize this conductive ink. We also extended this technique to twin wire sensor networks, where instead of printed materials, we have general sensors. And that's another paper, but I will be quick. And also another recent work is what electronic can do for measuring the bioimpedance of skin. So the conventional problems for measuring the bioimpedance of skin, especially viable skin and adipose tissue, are given by first the multi-layer structure of skin, which is clearly a complication for measurements, and second, the so-called stratum corneum dilemma. That is, the outermost layer of skin, that is the stratum corneum, is generally insulating. So this insulating stratum corneum prevents the easy measurement of the viable skin. So in order to solve this problem, we apply some theoretical analysis and also propose to use these normalized derivatives. But finally, what we found is that, yes, it is possible, at least in principle, theoretically, by using 4-wire measurements, similar to those we discussed previously, to measure the bioimpedance of viable skin and also of the adipose tissue. But this requires careful 4-wire measurements. Why? Because these parasitic impedances due to the stratum corneum are very high, and that results in large errors due to even small parasitics. So we theoretically analyze this problem, and we provide design guidelines for design circuits that allow to measure the bioimpedance of viable skin even without any injury or without any microneedles for penetrating the stratum corneum, so in a totally non-invasive way. And let me now mention another work that where we use electronics again for characterizing the nanowires in solution. So this is a standard approach, very complex, very beautiful, in fact, that has been proposed for monitoring the assembling of nanowires at single atom level. So it's beautiful. We could not make it because it's very expensive, requires very complex instrumentation. But we thought, there are also problems with that approach, like you need very high energy probing beams for possible artifacts, very expensive instrumentation, and only a single nanostructure level. So we thought if it was possible to monitor the wet chemical growth of zinc oxide nanowires in real time, in situ, with very simple approach. To do that, we just used a quartz crystal microbalance for drawing the nanowires. And as you see, we could monitor the frequency as a function of time. And with that insight, with just conventional wet chemical recipe, we could obtain very important information on the growth procedure and also design procedures that is better than the constant temperature procedure. So that is what we did, and we proposed that this monitoring online can be used for dynamic temperature synthesis processes instead of the conventional approach. So these are just examples of what the so many opportunities at the boundary between material science and electronics. And I would like to add that this is the traditional boundaries, because in fact, and this is the conclusion, universitas, university, comes from a Latin word that has to do with universe, with the whole, with the entire thing. So there are no real boundaries in science that is continuous. The boundaries are ours, and of course are very important. It's very important to define good boundaries for teaching. And so there are, yes, traditional boundaries. That's what I meant with traditional boundaries. So I think it may be time for new programs that contain more of this intersection. But even in the traditional program, it can be very important to strengthen the fundamentals instead of dedicating too much time to the specific, to the super specialistic things. Even they can be important, but still maybe we need to be very careful. And with that, I conclude my talk. Thank you very much.
Thank you, Chris. And we will leave the question answer to the end. And first, I would like to introduce our next speaker. Okay, let me share my screen. So our next speaker will be Professor Yunlong Zi, and let me introduce him. Professor Yunlong Zi is in the thrust of sustainable energy and environmental in Hong Kong University of Science and Technology, Guangzhou. Dr. Zhi received his PhD in physics from Purdue University in 2014, and his Bachelor of Engineering in Material Science and Engineering from Tsinghua University in 2009. Before joining HKUST, he worked as an assistant professor at the Chinese University of Hong Kong during 2017 to 2022, and a postdoc at Georgia Tech during 2014 to 2017. His current research interests mainly focus on high-efficiency mechanical energy harvesting through triboelectric nanogenerators, triboelectric effect discharge, GNG-triggered high-voltage applications, and a self-powered system. As the first and corresponding authors, his research studies have been published in top-notch journals, including Nature Nanotechnology, Nature Communication, Science Advance, etc. He was honored by Fellow of Institute of Physics in 2023, the MIT Technology Review Asian and Pacific Certified Innovators and 35 PR35 in 2022, Nano Energy Award in 2021, Fellow of International Association of Advanced Materials in 2021, and many other, honors. And without further ado, I would like to welcome our next speaker, Professor Yunlong Zi. Yunlong, and the floor is yours. And I will just, welcome Professor Yunlong Zi.
Okay, thank you, Professor Yang, and hello, everybody. Let me just quickly share my screen. I can see Professor Falconi just did a very nice introduction about the piezoelectric materials, zinc oxide and others. And so today I'm going to talk about some triboelectric related stuff. Especially how could we promote its performance, and secondly, how could we combine with different physics, especially the photons. Okay, so I'm Yunlong Zi. I'm at the Hong Kong University of Tech and Technology at Guangzhou, and this is actually a new university, and we have a lot of professors move from Hong Kong, and we are also actively recruiting many staffs like faculty and students, postdocs. So if you are interested, you may also contact me, and you also find the university website for the information. Okay, so I think I don't need to talk too much about the background. It's related to, especially with the development of Internet of Things. We have everything, wirelessly, highly distributed in every corner of the world. And the problem is, how could we power them? Because they are highly distributed. Then it's questionable if we are still using the cables, right? And if we are using the batteries, then the battery has limited lifetime. Then how could we sustainably power them is an issue. Then people think about the energy harvesting technology. So then the question is, how could we use energy harvesting to achieve a self-powered system? Okay, so what we are focusing is using the triboelectric effect, which is very commonly in our daily life. Then so that we can generate the tribal charge on the surface, and then through the electrostatic induction, as you can see from this animation, we can generate power. And then we call this a new device called the triboelectric nano generator. And thanks to my previous postdoc advisor, Professor Zheng Wang. And then I have actually worked on this field for almost 10 years. Okay, and here is some studies in my lab. I mainly work on the two things. One is how could we achieve high performance. Secondly, how could we combine with other physics, for example, photons. Okay, and while there are a lot of physics behind the triboelectric effect, especially how the charge was transferred, the charge transfer mechanism. Then people say that someone says electron transfer, some say it's mass transfer. Well, I didn't want to go to do too much details, but I still think the question is how could we characterize that? The very important thing is we want to find out what is the status of electrons after it transfer. So we take a look at its thermodynamic emission property, especially its barrier height W. Right? Because when there is with a different charge transfer mechanism, there should be different W after its thermodynamic emission, right? So that we can use this thermodynamic emission to determine whether it is electron transfer, whether it is the ion mass transfer. Actually, the situation is quite complicated. I find actually for many polymer-related materials, if the other material is metal, then it's actually majorly contributed from the electron transfer. But if you got the polymer to polymer, there's many different contributions from electron transfer and to mass transfer, and even the ion transfer could be, right? So, this is another very important thing. That is the breakdown discharge. Well, for if people ask me, what is your expertise? Like sometimes if he is not in the triboelectric field, I probably will say I will do the triboelectric for energy harvesting. And if people really working on the triboelectric nano generator or TNG, I actually will tell you I work on the breakdown discharge many years, right? So this is a very early work when I theoretically found that the breakdown discharge can actually make the almost half and even more energy harvested from the mechanical energy to be wasted through the breakdown discharge, right? So this is a theoretical work. But the question is, we know we can do the theoretical work just comparing the voltage to the breakdown voltage. This is simple, but how could we measure that? That's a question, right? What we actually developed the method how to measure that. That is through the calculation of the charge transfer and breakdown voltage simultaneously through our circuit-based methods, and then we can compare the measured result with the theoretical result. As you can see, it's consistent very well. Then so that we can actually control the discharge, right? We can on purpose discharge every time, or on purposely make it non-discharge every time. And so that we can actually calculate what is the real effective energy output per cycle from TNG, and then calculate the so-called the output energy density. As you can see at that time in 2019, we calculated the maximum value for TNG is almost 10 to 4 joule per meter cubic. Right. For your record, if you know about the lithium-ion batteries, the energy density for lithium-ion batteries is about 10 to 9. Right. So that's actually several orders to improve. Then the question is, how could we improve that? Right. Then we firstly think about it. Because there is a breakdown discharge, right? The first thing we want to suppress is the breakdown discharge. And especially that in the air, because the air molecules is very easy to have breakdown discharge. So we have some way. For example, we can increase the pressure, because with the increased pressure, we have the less mean free path for the electrons. And then with this short mean free path, the electron cannot accumulate enough energy to break down the L molecules, right? Okay, and then in that case, the breakdown discharge threshold was increased. Then the energy density can be increased to be about 1 to 5 order of joule per meter square. I believe this is still be able to cubic. I'm sorry. Still be able to increase further if we can suppress the breakdown discharge inside the material. So we are still working on that. And with this suppressed breakdown discharge, we can actually enhance the electricity generation, and then we can save more carbon dioxide. So this is some calculation. If we are using the TNG for the energy harvesting from the ocean, if we don't have any carbon dioxide field inside, as you can see, even though we have clean energy generated, but during the manufacturing and maintaining, we are actually wasting more carbon dioxide, right? And the total carbon dioxide emissions is still positive, which is not favored. But if we suppress the breakdown discharge through the fuel, the carbon dioxide inside and also with a high pressure, we can actually greatly enhance the electricity generation. And then the total carbon dioxide will become negative. So this is actually quite important for the, in the terms of the carbon neutrality strategy. And we also calculated the carbon emission per electricity generation from TNGs actually could be comparable to the biomass, could be solar panel for wind power. That means it can be a competitive way for energy harvesting from ocean in the future, right? Theoretically, actually. So this is about breakdown discharge. Another part of physics is the well, right? When you have material transfer, that means it has well. But the well or the friction well is not a preferred. We actually every time we want the charge generation, but we don't want the well, right? Okay, and the friction well will affect the long-term stability. The friction will affect the efficiency. The contact intimacy will affect the charge power output, which are all not preferred. So do we have some material interface that can have the trouble charge generation, but no well, no friction? Well, we found a way. We can use the liquid and solid for the triboelectric charge. Actually, liquid solid interface can generate a tribal charge, and we designed this structure. The water packaged inside the shell structure, let it shake inside, and what. But then another question is, the tribal charge generated from the water, that's not too much, right? And the charge density is quite low. And I have another question. Can we actually have some solid material? The surface property is like a liquid. It means it doesn't have the fixed crystal structure. It is amorphous, and even some atoms can be movable. At the same time, it can generate a large enough charge. Right? And then I found that could be the metallic glass, because it is actually naturally amorphous metal. Because it is amorphous, then the load is low frequency, low well. At the same time, it's a metal. And the metal is a contributor for the electron seeds, right? So it can generate in large enough electrons. So it can actually have a better charge generation. Then we can determine a term called the triboelectrification efficiency by the charge density over the friction. As you can see, as compared to the regular metal, it can be enhanced by the 4.3 times in the triboelectrification efficiency. That means we save a lot of energy during which was wasted through the wearing. And then we designed some device structure. We call it as OCT, offset charge transistor, like a TNG. Why is that? Because we can have offset charge generation on the left side to the right side. So this way we can generate a more charge density. At the same time, we use the transistor-like structure. That means we can control its charge release and charge holding. That means we can hold the charge to be the maximum value and then release in the one time to generate the high peak current and then generate a high peak power. And actually we generated the highest peak power density at that time, which making a new record. So now, because previously the lamps, which is over. And then how could we make the high energy, high performance TNG? And then second, as I said, we want to combine with other physics. For example, how could we combine with the photon generation? Photon is very important for the wireless sensing. Basically any kind of wireless sensing, either the IR, the visible light, or you use the electromagnetic waves. They are actually all photons. Then let's talk about how could we use the triple charge to generate photons. As you can see, traditional wireless sensing system has a lot of modules: the sensing, power, the signal modulation, the wireless transmission, which makes the structure very complicated and is large in size. But if we are using triple charge to generate the discharge, breakdown discharge, it means at the same time we can also generate wireless signals, which can be used for the wireless sensing. More importantly, this could be just a simple thin film structure. We don't need a battery, we don't need any cable, so we just use the finger sliding to trigger its wireless generation. Okay, at the same time, we can make the structure very small, right? Like a fingernail size. Could be distinguishable between the different devices. That means we can make it like a wireless ID for different items. Okay? We are actually working on some project, very interesting project. We can also make it a wearable, like the wearable devices for identification of people or the wireless sensing of some commercial sensors. Okay. Recently, we are also working on how could we combine with the existing technology. For example, how could we use that as a self-powered wireless metal detector, because we can, during the discharge, right, we can make it connected to a coil. Right. When the coil is getting close to a metal, it will agitate the eddy current inside. If there is eddy current agitated, then the inductance inside the coil, because the mutual inductance, will be changed. Right? When it changes, the wavelength, the spectrum of the generated the signal will be different. Right? Then we can use some way to detect the difference indicated. Then we can detect whether there is a metal or whether there is not metal. Okay, so this is how could we generate a wireless signal. And second question is, how could we generate the visible signal? Okay, so this is related to a kind of special material called the tribal induced electroluminescence material. That means basically when there is the electrical field generated by the tribal charge, there will be the lighting come up. But this is very interesting. But the question is, the light intensity is relatively low. And then we think about how could we use this, such a low intensity light generated from the tribal charge. Then we think about two scenarios. One is inside the ocean. As you can see here, right? Inside the ocean, we have a lot of ultrasonic waves, right? Then we design a device that can include a lot of the particles. When the ultrasonic wave come inside, the particle will oscillate by itself. Then it can generate a tribal charge top and down, and then we can have the light coming up. something look like this. Okay, and then through this light intensity, we inside the deep ocean, we actually can able to detect where is the ultrasonic source, whether it is from a submarine or it from the dolphin. So they are both possible. And we can also use this way to transmit the wireless signals, okay, by the 0101, right? Okay, and another probably possible situation is inside the human body. But the question, inside the human body, it is quite a wet environment. And if it is a wet environment, how could we trigger this issue? And then we think about we can utilize the tribal charge generated between the liquid and the solid. But then the question is, as I said before, the liquid solid can only generate a very small amount of charge density. Then how could we enhance the light intensity, right? Then we think about we can also have some way to enhance the instantaneous electrical field, even though with the small charge density. As you can see, we have the electrode structure, like a grating-like electrode structure here. Then we did some simulation. As you can see, when there is no grating electrodes, the electrical field change is actually pretty stable, right? And pretty stable, that means there's no huge electrical field, right? Then there's no huge intensity light, right? And then, but if there is some additional electrodes at the interface, when the water passing through the interface that with electrodes and the region without electrode, the instantaneous electrical field is becoming instantaneously very high. And with this instantaneously high electrical field, we can actually generate enough electrical field to trigger the light. Okay, so that's why during these demonstrations, as you can see the instantaneous light showing the interface between the liquid and the air. You can even see the air bubbles, and you can also sometimes see the particles inside the water. And we can sometimes utilize this light intensity to do the imaging of the biological species. Okay, so this is the possible applications. We can use the trouble-induced electroluminescence for biodetection. Okay, and then because the light intensity here is with a very short time, so then the question is how could we improve that? Right, we have some work recently about the material improvement. Right, the first question: how could we extend the intensity, the luminescence time? Then we can combine with some photoluminescence. For example, the SOAOED. Its function is it can actually absorb the light intensity from the electroluminescence and then release it slowly, so that the intensity luminescence could be extended to be like 10 seconds. Okay, at the same time, we use some additional ferroelectric material to enhance the local electrical field, so that we can have some acceptable about 10-second luminescence after you trigger. Okay, so this is another design we want to have. We call it as the self-powered visible platform for passive IoT. Passive IoT means a lot of sensors you don't need an additional power source. It's a passive, right? It can generate energy by itself. Now here, the energy could be generated by the TNG to power these sensors. But previously, if we are directly using the TNG to power sensors, that is one issue. During the different environment, for example, high humidity, your tribal charge generation is very small, and could be the half charge density. Then in that case, your sensor performance could be affected. Well, here we do some design, right? We have the reference channel. If the charge density is low, the current going through the detection channel and the reference channel are both low. Then the relative value between these two lighter LED matters. As you can see, the reference LED is always with a stable intensity, but the working LED, depending on your sensors, is changing with different resistors. Then we can utilize the relative light intensity between the two LEDs to determine what is reading inside your sensors. So this is some way we can avoid the misdetection inside the sensor of the passive IoT. So anyway, we have did a lot of work. So the two aspects, hopefully we can have collaboration in the future. And here I would like to acknowledge my students, the funding agencies, and thank you very much, and I appreciate any questions.
Thank you, Yunlong. And we will leave the question to the end. And
Okay.
next, I would like to introduce our next speaker. Okay. And so our next speaker will be Professor Yuebing Zheng. And Professor Zheng is from Mechanical Engineering and Material Science and Engineering at the University of Texas at Austin. He is holding the Temple Foundation Endowed Teaching Fellowship in Engineering. His research group innovates optical manipulation and measurement for the biological and nanoscale world. He has co-authored over 170 journal papers and one book, Nanophotonics and Machine Learning. He received his bachelor degree in applied optics from Nankai University in 2001, a master's degree in physics from the National University of Singapore in 2004, and a PhD in engineering, science and mechanics from Pennsylvania State University in 2010. He was a postdoc researcher with Professor Postwise at the University of California, Los Angeles from 2010 and 2013. He received the University Co-op Research Excellence Award for best paper material today, Rising Star Award, National Institute of Health directed the new innovation award, so that paid multi-million-dollar award, National Aeronautics and Space Administration Early Career Faculty Award, Office of Navy Research Young Investigator Award, 3M Faculty Award, Back Young Investigator Award. Basically, pretty much almost every award you can find in American for the young investigators. He is a fellow of the Optics, the Institute of Physics, and the Royal Society of Chemistry. Without further ado, I would like to welcome Professor Zheng, and the floor is yours.
Thank you, Professor Yang. It's my great pleasure to participate in today's discussion on multiphysics coupling and its applications in different technologies. So my talk will focus on the optothermal and fluidic couplings, and which lead to a new type of optical manipulation technology. So the work from my group mostly carried out by my students and postdocs, research fellows, some already graduated, along with our collaborators, and supported by different funding agencies. So progress in optics has led to a variety of technologies with different applications in many fields, including we just heard from Professor Zhi in his very cool self-powered optical sensors and optical emitter, like light emitting diodes, which also can be self-powered by exploring the coupling between mechanics, electronics, and optics, as well as Yuebing for my talk is optical tweezers, and which won Nobel Prize a few years ago for their breakthrough applications in understanding biology. Typically, optical tweezers rely on optical gradient force, optical scattering force to trap or confine micro nanoscale objects at the focus points of the laser beam. It can control manipulated particles in 3 dimensions, which can be controlled by a computer automatically. Since we're using light, it can be remotely operate those manipulations. Although many breakthroughs enabled by the traditional optical tweezers, but there are some limitations which prevent their further applications, including just a few examples. So typically, because it's a working mechanism relying on optical forces, and which are very weak, so a high power laser beam are usually needed to operate to manipulate and trap the particles. Also, since it's a basic optical phenomenon, it requires a good contrast between the objects we are going to trap. For example, this colloidal particle here, and typically it's in the solution, so the solvent. So it requires a good optical contrast, typically, which means the refractive index of this particle that to be trapped by laser beam and the refractive index to be have some difference. But in some cases, like in biology, the biological cells and the solution, like the water, they are very similar. Refractive index make more challenging, so even require even higher power to do that. But when the size of these particle or organs go smaller and smaller, the power requirement is even higher. So this higher power could damage some fragile organs or nanoparticles like polymer particles. And in many of these operations or manipulation, typically what has been achieved is mostly translational along X, Y, Z direction. But in some cases, the rotation of the objects might be needed for some fundamental applications. But using traditional mechanism, it can be achieved for rotation of particles, but maybe need a very complicated structured light or some unique which have unique optical properties, which are not common to many of biological cells, for example. So this limitation motivated us to look into different mechanisms to develop optical manipulation technologies. And one of the direction in our group is focus on exploring optical heating effects. Optical heating. So in many cases, in particular optical tweezers, heating typically try to be avoided because the heating will reduce the trapping stiffness of the particle or cells, but the heating could also damage biological cells. But in the next few 20 minutes, I'm going to show you that by harnessing the optical heating can lead to improved manipulation technique. In particularly, by coupling optical heating and the fluidics behavior, we're able to show that what we call heat-mediated optical manipulation enable us to reduce optical power for the manipulation, and we can using much simpler optical setup, because in traditional optical tweezer, in order to achieve a good trapping, typically we need a high power laser, but also high quality laser beam. And also we need highly focused this laser beam using complicated optical systems. But here using heating effects, we can make this system become really simple. We can even using incoherent light, white light, or even the laser point. Typically we use for presentation in poser to achieve the manipulation. So that's make these tools accessible to more researchers beyond those labs with sophisticated system. And further, this type of manipulation will have expanded manipulation mode. As mentioned, not only translational, rotational, even more, as I will mention later. Also, the expanded working environment. Here, working environment means not only we can achieve the manipulation typically in the solution or in the vacuum, in the air, as traditional optical tweezers have achieved. We also show that we can move this from liquid into solid phase, and we can achieve this on the solid substrate or even in the solid bulky environment. One direction, which is the three themes that I will talk today. So one theme is exploiting the thermophoresis effect. So we're using laser beam to heat the media and create temperature gradient. So under this temperature gradient, the particles or cells will move along certain direction, either from hot to cold region or cold to hot region under this gradient. But the challenge with these thermophoresis effects in optical manipulation is that in many cases, the movement typically will be from hot to cold region. But in a lot of cases, the position which is irradiated by the laser beam become hotter. So you are thinking that actually the laser beam is pushed away the particles rather than trap it. So that is not what we expected for optical manipulation. So a good example shown is by Professor Frank Citral's group in Germany that take advantage of these thermophoresis by using the gold nanoparticles as shown here as a triangle. When the laser beam hit the triangle, it's a metal, in particularly it have surface plasma excited at this specific wavelength, so generate a strong heating effect. So the particle position will become hot, but when you go away, it becomes colder. So this white ball is the object they are trying to trap. So you can see instead of being trapped at this laser beam position, actually the particle is pushed away. But they are make a very smart move to show that by arranging these metal particles in the ring configuration, so you can define a cold region in the center of this ring, and you can confine this particle in this cold region and be trapped there. But this is a very nice demonstration to show that thermophoresis will drive the particle from hot to cold region, but they are not good enough to achieve a dynamic manipulation of these particles. Here is just the static confinement. So we overcome this limitation by looking into a phenomenon called optothermoelectric effect. Simply speaking, as the figure D shows here, this is cross-section, and we have a substrate which can absorb light and turn light into heat. And this is a solution. In this solution, we have the particle is a white ball that we are going to trap using laser beam. But we added a little bit additional things in this solution. We added called a surfactant, the CTSC. This surfactant molecule serve a few roles. So one role is they coating the particle, so the particle become charged, positive charge in this case. Another role is at the cell, this cell, the small particle made of this molecule only, so they also have positive charge. And in this solution, we also have these negative chloride ions, which have negative charge. So we have so many different, three types of particles with different charge in the solution. When we hit laser beam in the figure E, we create temperature gradient. So at the center of this substrate, it's getting hot. When you move away from this center, it's become colder. So you create this temperature gradient. And we know traditionally, conventionally, this thermophoresis will drive all the particles away from this hot region, away from this laser beam position. But interesting phenomenon happen is that this micelle move faster and the ion moves slower. So when time goes on, there's a separation between positive missile and the negative ion. And we know this is a create electric field. And the particle have positive charge. So you can see that there's electrostatic force, there's electrical force to trap the particle at this hot region. And so that's a basic principle of optosomal electric nanotweezers. So using this principle, we are able to reduce the power for trapping the particle about 1,000 times compared with conventional optical tweezers. But more important, this trapping mechanism can apply to all sorts of particles. In traditional optical tweezer, we know it's very challenging to trap metal nanoparticles, in particular at the wavelengths which close to the plasmonic resonance. As I just mentioned that because of this plasmonic excitation, the particle become very hot. So under this heated condition, the Brownian motion will become so strong, the trapping will become almost impossible. But using our mechanism, we are able to show that we can trap all type of particles, including metal nanoparticle at plasma resonance wavelengths. Another interesting thing using this new mechanism is that we are able to introduce interparticle interactions through what we call artificial bonding. And this artificial bonding enables us to bring the particle together and make them stay there, stick together. In conventional optical tweezer, whenever we turn off the laser beam, the particle will go back to Brownian motion again. When you bring two particles together, try to stick them to create a new materials using these particles as a building block, you have to introduce a very special interaction. But in our system, it's become intrinsic force embedded into this system, and we call attractive depression force. It's because of the missile. And when we bring two particles close enough, the missile cannot fit into the gap between two particles. And so the unbalanced concentration of a missile will push these two particles together and to form what we call the artificial bonding. In plasmonics, we all know that when you bring the two metal particles together, the coupling between them can introduce a new mode of a surface plasma resonance. And the one is longitudinal, and one is a transverse mode. So we can easily monitor the coupling in real time. And this coupling is tunable. In solid state physics, we know the bonding between atoms to form solid materials is fixed, like carbon-carbon bonding, covalent bonding, which is you have specific distance between carbon-carbon. But in this artificial bonding is tunable. It all depends on the concentration of the missile you add. So basically, you are able to achieve the distance between the two particles continuously changed. So if we explore the coupling between two particles, this distance control enables us to tune the optical property in this case, and we can achieve tunable materials. In the next few slides, I will show you a few examples for application of these optosomal electric nanotweezers. So demonstrated by Professor Yuan's group in China, and they're using this optosomal electric tweezer to trapping golden nanoparticles, since this is applicable for all sorts of particles. And once you can trap this nanoparticle, because of the surface plasma effects, people has been broadly explored these effects to enhance the Raman spectroscopy that we call surface enhanced Raman spectroscopy. So they demonstrate that since you can use a laser beam to manipulate the particles through the optosomal effect or optosomal electric effect, and you can move this around using as a prober, as a Raman prober. So they can enhance optical mapping of these 2D materials in the solutions and give you a high resolution mapping and without actual contact measurements. So this is one very interesting application of these tweezers. In our lab, we're using these tweezers to achieve the assembly of new nanomaterials using colloidal particle as a building block. So as I mentioned that so far we have achieved the capability to trapping the particle, but also can bonding the particle together. So this is just like the way we play with Legos, using hand to hold the Lego piece, bring them together, and using the locking mechanism to create all sorts of architectures using Lego piece as a building block. So if we imagine this Lego piece of artificial atoms or colloidal atoms are many chemically synthesized micro nano structure as a building block, and we're able to bring them together using the depression force to bond them together. So this creates what we call superstructure, or in some field people call metamaterials or metamolecules, which show very interesting optical property or acoustic property, which different from conventional bulk materials. Just a quick video to show you how we do the manipulation in the real time. So this is in parallel. We can split one laser beam into several beams, and each beam can trap one particle. Or we can do it in series fashion. So the advantage here is clear that whenever we bring the particle together, the depression attractive force will bond them, stick them there. When we move away the laser beam to capture another particle, and the originally assembled structure still stay there. So that we can build whatever shape you like by putting one particle at one by one. So just give a kind of summary of what we can achieve using these tweezers. And we can apply to all sorts of particles, different size and different composition, which means different materials, metal, semiconductor, dielectric materials, polymers, and we can create all sorts of architecture. And we studied the optical property of this superstructure and show very interesting properties compared with individual particle or the conventional bulk material. So another application, since we can now using low power laser beam to trap a particle, so which means within the same power compared with conventional tweezer, we're able to trap many more particles. So the enough large number of particles enable us to use them as a platform to mimic, to study collective motion. As collective motion, which you may be familiar, which we observe in a school of fish or a flock of birds or even ants, even in human beings. This very collective motion is very important for survival of many of these animals and to get food more efficiently. But the mechanisms for different type of collective motion still not very clear. And using our platform, we're able to actually to parametrically to change the interaction between the individual particles, which represent individual birds, for example, or individual fish, to understand how the collective motions are formed, or what the working principle. So in our recent study, we actually show that a very simple algorithm of very simple rules to align the neighboring particle, their velocity at any moment, which can drive the collective motion. This working principle might be the foundation for a few of those collective motion observed in nature also. But in another direction, by achieving this collective motion in this artificial system, we are pushing into micro nano robotics applications. And we or other researchers believe that by exploiting collective motion, we're able to, for example, in micro nano robotics, in nano manufacturing field, can achieve the manufacturing of a larger system in a more efficient motion by making them collaborate in a more efficient way. And this working principle can also be applied to autonomous cars or autonomous drones and to avoid the traffic in a better way through these collective motions. And we can even expand the operation mode. In conventional optical tweezer, typically translational motion or rotation in some special case. And we show that in this optisomal manipulation, we can achieve to the particles we are trapping, we are interested to manipulate. So just give a quick applications. Once we can achieve this rotation, what kind of application can be enabled by this new operation mode based on simple optics. So one application is by rotating these biological cells, organisms, we can using standard optical microscope to achieve three-dimensional mapping. And even we can combine machine learning. So this three-dimensional image we take from these biological cells, and we can training the machine learning algorithm which become very hot field to not only identify the image for disease diagnosis, for biological understanding, but also for inverse design of many nanophotonic structures. Recently, we write this book to show how the many exciting technology can be achieved by integrating nanophotonics and the machine learning. But in this example, we show that because we can rotating the cells, we are able to capture many images from one single cell. Because in machine learning, one big challenge is training data. In many cases, the machine learning is powerful, but the training is really a very challenging, tedious task. You need enough data to train an algorithm so they can apply it for the actual situation more reliably. But in many experimental situations, getting enough data becomes very challenging, including this optical imaging for the biological cells. But through this rotation trick, we're able to from much less cells to get enough training data, even the accuracy even higher than using a larger number of data and larger number of samples. So that's give the training become easier. And by using this machine learning, we're able to get to distinguish the strains of the same type of bacteria in the high accuracy. More application example using rotation capability is that actually we can monitor the rotation behavior of the cell when they interact with the substrate to understanding the adhesion between the cell and the substrate. Cell-cell adhesion or cell-cell communication is play a fundamental role in biology. By measuring its adhesion become challenging. Even more challenging is for shear interaction, which in this case, rotation can lead to that information. By monitoring this rotation behavior, we're able to get the adhesion behaviors for different type of strains of bacteria. So one more example is recently by Professor Zheng in China, and they show that by combining optothermal tweezers, the capability to trap the particle at this laser beam, but with the CRISPR and able to achieve the detection of a single nucleotide using optical approach at high, very low concentration. But you may question why these heating effects may be damaging the particle because it's rely on heating, right? So some biology cell don't allow at all. So we circumvent these heating effects by two strategies. One is we can cooling the whole solution, what we call hypothermal optothermal theoretical tweezers. So when you're cooling down the environment, so even though you heat it locally, the actual temperature at this biological cell still within its comfortable zone. But another interesting thing by cooling down the temperature is that actually you can flip the motion of a particle from hot to cold region, or from cold to hot region. So in this case, you don't need add a surfactant like CTSE. In our former example, you can still achieve the trapping using the optothermal effect. Another approach is simply using laser beam instead of heating the substrate, we can cooling down. And so that's a very exciting field using laser beam to cooling down solid state materials. As we show that in this special substrate, when your laser beam hit it, it can cool it down. So at the laser beam, you have a colder temperature, a lower temperature. So normally, a lot of particles will move toward this colder region. So that's the first category. The second category, I will go quickly, and you can purposely increase the power of a laser beam, so you can generate a bubble. When you generate a bubble, you create what we call Mongolian convection. So bring the particle to the bubble and stick to the bubble. When the bubble collapses, the particle will stick on the substrate. Now, so we can use these to create a printing technique.
Just like Knight Rider when they used to drive into the back of the moving truck.
Yeah,
This is basically that.
exactly.
What's old is new again. To Texas now, where scientists have mastered another difficult maneuver. No Knight Rider, but it's pretty good. How do you manipulate microscopic nanoparticles? Well, it's simple. You just trap them in a micro bubble and then use a laser to move them around. That's what engineers at the University of Texas are doing. They call their technique bubble pen lithography. Moving the nanoparticles around with bubbles avoids handling them directly, and that lowers the risk of damaging them. And these are great tools when scientists want to start building their tiny futuristic machines.
So we can not only manipulate particle, print the particle substrate, but also this can apply to ions. You can concentrate the ion at the bubble interface, which form a microreactor to drive the chemical reactions in the real time. And this, because of the high concentration effect, the microreactor effect, we can also induce a chemical reaction which conventionally cannot be achieved. So you can achieve very interesting new materials which show very good analytical property, in this case, the nanoalloys, or the metal structures to form the building block for metal surface or metal material. We can also use this bubble to concentrate molecules for the optical sensing applications. The example show that using a very special chiral substrate combined with the bubble concentration, we're able to detect the metabolites in the urine and to detect the diabetes. And we show that this can be achieved a similar sensitivity by using glucose conventionally to detect the diabetes. In this case, we detect the chirality change of metabolites in the urine using these very interesting chiral metal materials by combining the bubble concentration so that the throughput can be higher and the sensitivity can be increased because of the bubble concentration effect. And we collaborate with Professor Zheng, which just gave a greater talk on pushing the resolution of femtosecond femtosecond laser beam-based manufacturing in last week from Tsinghua University, and also with Professor Lin Lin, who was who did the postdoc in my group, who invented the optothermal electric tweezers, bubble printing, and many other techniques before joining Tsinghua University. So when he joined there, so we continue to collaborate using femtosecond laser beam actually to induce a bubble, and we can print in these particles on the insect surface. So this enables us to using, this is magnetic particle. So you can use a magnetic particle, a magnet, to control the behavior of these insects. The last scenario, the third one, is to show that using thermal effects, we can expand the working environment. So we can move the manipulation from solution to the substrate. Here I show you is we call the optothermally gated photon nudging to achieve manipulation particle on the solid substrate. The working principle is like this. So you have gold particle, this is a cross section on the substrate. Between them, we put a CTSE layer. When the laser beam hit the particle, it gets heated up. So this layer, CTSE layer, becomes cozy liquid phase. So the friction between the particle and substrate become weaker. So we can use a scattering force from the laser beam to push the particle. So example show we have this silicon nanowire. We can use in this method to push the silicon nanoparticles to the silicon wire along the wires. Depends on position, they show very different color response. The very interesting optical property can be controlled by simply control the position of the silicon nanoparticle along the silicon nanowire. We can even achieve a motor effects by controlling the size or shape of the particle, their relative position with the laser beam. So this model, typically we achieve a micro nanomole is in the solution, but here it's on the solid substrate driven by a single laser beam. Even we can move into three-dimensional in the polymer matrix to achieve three-dimensional manipulation of the silicon particle here. So we can create a very interesting structures using this silicon particle as a building block to create in three-dimensional version. So as a conclusion, and the field of optothermal fluid coupling can lead to the new capability to manipulate particles, cells in the various mode, and depends on the light source, medium, what kind of substrate. There's more phenomena we can explore beyond what I just mentioned, the thermoelectric and the optothermal flow. Then like photophoresis or diffusion fluorescence, even deformation can also be induced by the optic heating effect. So understanding these fundamental physics at this multiphysics coupling regime, and we got enabled to control more operation mode. This different operation mode, of course, can be very straightforward. You can imagine as how we operate the micro nano robots, but they can also exploit it in other fields, like in drug delivery, create new materials for optical sensor applications. And I believe that with more understanding of this fundamental, more new technology application can be demonstrated in the near future. Thank you.
Thank you, Professor Zheng. Very nice talk. And next, I would like to bring our panelists, here. Thank you. And I would like to, introduce our next the panelist, and Professor Yuebing Wang. She is from the School of Advanced Materials and Nanotechnology at the Xidian University. She received her PhD degree from the School of Chemistry of Nankai University in 2018. Her research mainly focuses on the design and construction of bursting electroactive coordinated polymer and devices. Her work has been published in Advanced Functional Material, Nano Energy, Chemical Engineering Journal, Chemistry Science, etc. And welcome, Professor Yuebing Wang. And next, I would like to introduce our next panelist, Professor Yunlong Zi. He is a distinguished professor of Cheng Kung Scholar Program in School of Materials and Energy, Lanzhou University. He got his PhD degree of Material Physics and Chemistry in 2004, Lanzhou University, and then worked in Lanzhou University until now. From 2007 to 2009, he worked as a visiting scholar and postdoc in Professor Zheng Wang's research group in Georgia Tech. He mainly works on nano-energy technology, sensors, and self-powered nanosystem. He has published more than 120 scientific papers on Nature Nanotechnology, Nature Communication, Advanced Material, etc. And I'm very happy to have our panelists here. And now let's open our panel discussion. And so Professor Yun and Yuebing, and maybe if you want to ask any question to our speaker, and you may go ahead. And maybe I can get started. Let me kick in. And I'm really impressed by all three speakers' work. First, let me ask Professor Zheng. And very nice, you are using the laser, and instead of using the tracer, you have developed a new technology to manipulate the particles. In addition to that, you can also build some system. That's truly impressive. Here, just one quick question is, look like you're depending on the charges to bring particles together, right? And later, you also talk about you have some built-in lock-in system so that to hold them together. So my question is, after you bring all those particles together to form a kind of arrays, how long they will stay, together stably? They will stay there forever, or they will just, separate due to the Brownian, motion?
Yes, so it depends on the concentration we added of the CTSE. But this CTSE, as I mentioned, not only introduce this bonding, but its concentration will affect the distance between bonding, but also, as you mentioned, will affect how long this bonding will last. If you introduce at a high concentration, the bonding will be stronger and it could stay longer. But it also depends on the environmental temperature, as you just mentioned, the Brownian motion. So if the whole system, the temperature higher, the Brownian motion stronger, the chance to break the bonding will be also higher. And typically, under our typical experimental condition, a few hours will be no problem. And so that's enough for us to do all sorts of study between interparticle interaction, how they affect optical properties. But for permanent use, you have to introduce more approach that, for example, is a photoresponsive polymerization process to fix the whole things in the permanent way. Yeah, it's a dynamic system, but give us actually opportunity to reversibly control the particle. We can create all sorts of shape, use the same type of particles, and to study how the structure affect the properties.
Okay, great. Thank you.
Zheng, I have one question for Christian.
Yeah, go ahead. Yeah.
Okay, thank you. Hi, Chris.
Hi,
very nice talk. Yeah. You just said you can monitor the growth of zinc oxide nanowires using force balance, right?
Yeah. Yes.
Yeah. My question is how to realize that, and what kinds of characters of nanowires can be monitored? Thanks.
Thank you. Very nice question. So the yes, there is you need to take advantage of the technique. You need to grow the nanowires on top of the quartz microbalance. I'm not sure if I can share the monitor quickly. Sorry. Here. So one key to this technique is that you need to to be able to grow the nanowires on top of the quartz crystal resonator. And that was very simple in our case because it was just zinc oxide nanowires, and they can be easily grown on these silver electrodes. So these are the silver electrodes of the microbalance. And you just, with a conventional wet chemical approach, you can find details in the manuscript, then zinc oxide nanowires will grow. So very simple wet chemical process. But let's say in many other processes, of course, it can be more complex. So we didn't need any seed layer or anything. This is just a SCM photo of where you see the quartz and the zinc oxide nanowires that grow on the silver electrode without any seed layer, just wet chemical. So in our case, it was very simple because of this selection. So this is actually just a conventional commercial quartz. So we just open the cap and we have the silver electrodes we place in the wet chemical solution, and the zinc oxide nanowires grow. So as long as they grow, the resonant frequency of the microbalance will be reduced because of the increased mass of the electrodes, and that is how we can monitor. But more in general, you can use the same approach, but yes, it depends on the type of nanowires you want to grow and to monitor, and also on the type of substrate. I'm not sure if this answers your question.
Thanks, Chris. I think you can easily measure the weight of the nanowires, right? But how to measure the morphology and other characters of nanowires?
Thank you. Very, very good question. Of course, this approach must be combined with the conventional SCM approach. So in order to design this process that we came up with, also the dynamic temperature during the growth. So not constant temperature, but we use 90 degrees Celsius to start the procedure and then 70 degrees Celsius to keep the process going for longer time. So that was the process we designed. But to do that, we combined the information that you can have with this technique with the conventional SCM images. So it's not sufficient for everything. For instance, just to give you an example, let's see this figure A at the top left. So in blue, you see the temperature. So we cycle the temperature from room temperature, slightly less than 30 degrees Celsius, to the high temperature required for promoting the growth of the zinc oxide nanowires in solution. so about 90 degrees Celsius. And then we bring the temperature back down, then back up, down. So temperature cycles. And here you see the resonant frequency of the quartz crystal microbalance. So it starts constant. Then when temperature goes up and the nanowires start growing, the resonant frequencies start going down. But then we go down with temperature, and that means that the growth of the nanowires will stop with some time. And therefore, you see that the resonant frequency becomes more stable. Then we increase temperature again. So again, fast growth. And then we reduce temperature again. So just to give you idea of the type of information that you can have, but it's not everything. You need to combine with other approaches like we used in combination with SCM images.
Okay, I see. Thanks, Grace. Thanks
Thank you
again.
very
Great.
much.
And yeah, by the way, for all the audience join the program online, you may also type in your question, and you may ask a question to any speaker here. So do not lose this opportunity, and you may type in your question online. I will read it for you.
Yeah, Professor Yang.
Yeah, go ahead.
Yeah.
Please.
I have a question for Professor Zi.
Oh, thank you.
Thank you. I'm a newcomer in this field under the guidance of Professor Yang. I just tried to use metal organ frameworks in TNG. We tried several works, but I would like to ask you about how you view the application of porous materials in TNG.
Porous materials.
Yeah.
Well, I think porous materials could be good for because they can effectively increase the contact surface. So maybe the charge generation could be enhanced. But there is another issue could be related to porous material. That is because the porous materials, there's a lot of air gap inside, right? The air gap is very easy to have breakdown discharge. So the physics could be like it generate charge continuously and then discharge continuously. So I think if you can have some way to suppress the discharge internally, but generate a charge continuously in the surface, that would be good for the performance.
Yeah. Okay. Thank you. Thank you.
Just some initial thinking, right? But of course, it still depends on your experiments, right?
Okay. Okay. Thank you.
Okay, great. And also for all the speakers, maybe you can also ask each other if you like. And maybe I can ask.
Yeah, I have a question for.
Go ahead, please.
Yeah, I have a question for Professor Zheng. Yeah, I like your work about the nano tweezer, but my question is about the limit for the tweezer. Right, you can move the particles, but how small size you can move for the particles?
Yes, that's the exact question we received from the review for our Nature Photonics paper before we get finally accepted. So at the initial demonstration, we showed that we can kind of trap maybe about 100 nanometer particles, but they asked the question, so we try to demonstrate more. So we went back to the lab to show that actually we can push it to 20 or 30 nanometer, but we can push further. Theoretically, we can trap any type of how small particles. But the challenge is how we see these. So the limit is by the imaging capability, and with metal.
Oh, imaging capability.
Yes. So to see individual particles, to see whether the trapping happening or not, right? So we need to monitor where the particle is, and to monitor this actually be trapped.
But the imaging capability limit is like hundreds of nanometer if you are using visible light.
So that's a trick. If you're using plasmonic particle, I don't know how much familiar with use plasmonic. So some metal nanoparticle, they show very strong resonance at a certain wavelength. So at that wavelength, they can scatter light strongly, right? So if the plasmonic particle, if we're using what we call dark field scattering microscope, so dark field, which means you only detect the scattered light from the particle. So using that technique, because of the metal particle can scatter light strongly, and because we're using this dark field, and we can only detect the scattering light, so we're able to see those brightness of the particle, even at maybe 20, 30 nanometer.
Oh, 20, 30 nanometer, okay.
Yeah, we can demonstrate that. But if it goes too small and the signal too weak, so we cannot see. But theoretically, the size was not a limit.
Yeah, a follow-up question is if we are, changing the wavelengths. For example, we can make the wavelengths even smaller. Like, for example, you use UV or even something like X-ray. Is that possible to make it like a atom size?
Oh, so you're also talking about you're talking about the confinement, how small region you can trap. And yeah, you make a very good point about the diffraction limit, right? So when you say you're using shorter wavelengths, it's because the diffraction limit will make it you can confine the region with shorter wavelengths. But, in our working principle is using temperature gradient. So we look into how strong we can confine the temperature gradient to achieve how strong we can confine the particles. Right? So the laser beam hit the substrate, but the temperature distribution will also decided by not only the laser beam size, but also the thermal conductivity of the substrate or the thermal conductivity of the solution, because it will dissipate. Right? So we need to engineer the substrate to achieve strong confinement, to trap even smaller particle at a small region.
But theoretically, this is possible, right?
Theoretically, we can use a single particle as a heating source, single nanoparticle as a heating source, right?
Okay.
So we can maybe can confine this temperature, the gradient strong enough at maybe below 100 nanometer, but even go smaller has been challenging for that. Yeah, at atomic level might be very challenging. Yeah.
Okay. All right. Thank you very much. I think it's very interesting.
Thank you.
Any other questions? Okay. Maybe I can ask Professor Chris Falconi a question. Earlier, you talked about you have a material you can change it from for the pyrielectric material. You can change its coefficient from the positive and to negative. So for that part, maybe a little bit lost. What's the mechanism so that you can change its coefficient from the positive to the negative?
Very good. Thank you very much for this question. And in fact, the model for these LDH pyrielectric nanogenerators is likely to be very challenging. So there are very many reasons to think that these LDH will be ideal candidates for designing pyrielectric nanogenerators, but the physics may be quite complex because there are many unknowns. For instance, this LDH, we know that when we change the divalent cation or trivalent cation or anions or divalent to trivalent cation ratio, the structure will change and also the band diagram will change. And how will it change? So the way you can model is by performing single atomic level simulations, which of course is quite complex. And in fact, your results will depend on the specific choices of the divalent, the metal cation, the trivalent cation, the anion, and their decomposition. So, for instance, the divalent to trivalent cation ratio. But in the real structure that we designed and we fabricated, we have gradients of the composition. Oh, sorry. We have gradients of the composition, and that means that, for instance, the band structure will depend on the position in a way that is not easy to predict. Not only the band gap, but also the minimum level of the conduction band and also the top level of the valence band. They will all depend on the position, and in a way that we can measure in some way, but still we don't have all the parameters because, for instance, we don't know how much water is within the layers and the exact concentration of the anions. So there are too many parameters and a very complex system. So that's why in this paper we did not propose a model for the pyroelectric nanogenerators that is a clear indication, but we just restrict to giving the main reasons why we can expect the pyroelectric behavior and also that is widely tunable. So these reasons include the size effects, the composition gradient that has been shown previously in literature to give rise to a strong pyroelectric effect, and that the asymmetry between the top and bottom, so that we expect there is some polarization that, of course, will be temperature dependent. So we give the main reasons, and we did not just give a clear quantitative model for this device. We can only say there are reasons to believe this is pyroelectric because of several reasons, and we experimentally verified that. And we also verified that if you just change the divalent cation, you can get positive or negative pyroelectric coefficient. But quantifying that, we are not able at this time. So we need more time, maybe much more time. Well, thank you for the question.
Yeah,
very interesting.
Yeah, great. Thank you
I have
so
a
much.
question for both Professor Zhi and Professor Falconi, since both of you have done great work on the nano generators. So can you describe in the maybe near future or far future in which that the nano generator, how it change our lifestyle most dramatically? What kind of scenario?
I think Yunlong will start.
Say again?
Maybe Yunlong can start.
Oh, okay.
Professor
So,
Zhi. Yes, please.
Please answer the question briefly. We ran out of the time.
I think I think the nano generator, because it harvests small energy in the world, so I think it's mainly for, especially for the Internet of Things, very many small devices. At that time, if everyone can equip it with a nano generator to harvest small energy, that could be useful in this way. So generally in the micro energy scale.
Okay.
Yeah.
Okay, great.
Yes.
Yeah. So due to the time limit, look like we have a lot of to discuss, and probably we can host another program in the future. And next, I would like to conclude this panel discussion session. And first, I would like to to deliver this electronic certificate of gratitude to Professor Chris Falconi for his great talk on the opportunity at the intersection of material science and electronics. And Professor Falconi, thank you very much.
Thank you.
And,
thank you, all of you. Thank you.
Sure. Next, I would like to thank the Professor Yunlong Zi, and for his great talk on the high performance triboelectric nanogenerator and tribophotonics, and he is a kind of a certificate to you, and thank you very much.
Thank you, Professor Yang. Thank you, Professor Qin, and the hosts.
And last, clearly not the least, I would like thanks Professor Yuebing Zheng for his great talk on the how to train in optics, and look forward to talk all you guys in person in the future. Thank you, Professor Zheng.
Thank you.
And here will be the next week's program. Next week we still have the youth talk, and I really look forward to this youth talk, and hopefully we have all the audience attend next week's youth talk as well. And thank you. That'll be all for today. And I will thank you so much for everyone. Bye bye.
Thank you. Bye bye.
Thank you very much.
Great talk.
不再是奇迹，不再是幻想，此刻真感觉全世界对我鼓掌。不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞。不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can。没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can。你也能够像我一样飞越最高山岗。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。能够像我一样飞越最高山岗。
祝你生日快乐！该吹蜡烛了，来，我帮你。啊！祝你生日快乐！生日快乐！
好漂亮的花，我很喜欢。
这是我的礼物，多层陶瓷电容器。
哇，这是多层陶瓷电容器吗？
失败了，没新意。
那个我的也是啊。
哇塞，这个不是太阳有电的多层陶